Znači da pala se od ovoga sporta. Šta je to?
Okay, I think we should start. Ladies and gentlemen, it is my great pleasure to introduce and to announce this session. We have a keynote speaker, Professor Eleni Hadji. Let me say a few words about Professor Hadji's biography. She is Associate Professor at the Chair of Structural Mechanics and Monitoring at Swiss Federal Institute of Technology, ETH Zurich in Switzerland. She got her PhD at Columbia University, New York, USA, and has won many prizes and awards for her work, such as 2020 EASD Junior Research Prize, awarded by EASD, then 2020 Walter L. Huber Career Prize, awarded by ASCE 2019. Then TUM Hans Fischer Fellowship, awarded by the TUV Sud Foundation, and many more. Professor Hadji is director of the joint ETH-ZUZH PhD program, Computational Science, Zurich, and module leader of Dynamic Mobile Sensing Platform, and principal investigator of automated hazard detection for social resilience. She is editorial board member of many journals, such as Journal of Sound and Vibration, Structure and Infrastructure Engineering, Mechanical Systems and Signal Processing, Structural Monitoring and Maintenance, Archive of Applied Mechanics, and more. She is doing research in the field of data-driven assessment of engineered systems with special interests in identification and control of nonlinear structural systems, structural health monitoring, life cycle assessment and damage detection, smart sensor technology, smart materials and structures. Today, she will present the lecture which is entitled Augmented Twins, Physical and Data in Support of Virtualization Structural Systems. Professor Hadji, the floor is yours.
Thank you very much for the nice introduction and for giving me the opportunity to present a bit on the vision and work in the Chair of Structural Mechanics and Monitoring at ETH Zurich. And so what I will be discussing today is the topic of structural health monitoring, which in our group we treat as a chain of basic operations initiating from the collection of data or information from structural systems that can be achieved through different types of low-cost technologies that are today increasingly made available to us also for deployment of large-scale systems with the purpose of diagnosing and prognosing the condition of these systems. And by diagnosis, I am referring to the investigation of the condition of the system as is, whereas with prognosis, we're trying to infer a prediction of how this will evolve in the remaining useful life of the system. Now, in doing so, we need to translate raw data information, and perhaps the biggest tool we have as engineers in our disposal for doing this are simulation models. So I will discuss a bit on this also later on as to how this can be conceived as a link between pure or raw data and information. And then finally, I would also like to show a glimpse as to how we use the indicators we develop from data and models for managing the operation, maintenance, and overall behavior of structures at the system level. So here you can imagine not only individual structures like wind turbines or bridges, but their assembly in a roadway or railway network or in a wind farm setting. So this is a small overview of how we get our data, or at least the use cases we work on at the chair, starting from collection of data from railway infrastructure, which we do by using sensors that are deployed on vehicles, such as trains, for assessing the behavior of both the vehicles and the infrastructure that is traversed. Of course, we also have cases from, let me go one step back, cases from traditional civil infrastructure, which is essentially the deployment of sensors on bridges and building structures, from industrial assets, because machines are also structures for us, and also increasingly from wind turbine structures, where a large portfolio of our data is now being collected from. So here you actually see one of the wind turbines that are owned by our group and which we're using as a living lab to develop new research directions. But what I will be discussing here today is actually related to the middle link of that chain, which has to do with the aspect of monitoring and simulation, and I would like to discuss why this is important. Before I can do this, however, I would also find it meaningful to explain what you can do with data on its own, just purely relying on information that is collected just from sensors, but without necessarily using the physics that lies at hand. And for doing this, I will show you an example from wind farms. This is a very famous picture which shows the effect of wakes, which is basically the effect of the positioning of turbines within a wind farm, where the front row turbines have a different exposure to the wind than those that are in the shadow of these front-facing turbines, where you have this wake effect. That means not only a lower speed that is reaching the turbines that are in the downstream, but also cyclic loads that are adverse and which would impose higher loading on these structures. Now, to generate a physics-based model about this phenomenon is doable, has been done, but of course is taxing and is very approximative. You can use refined computational fluid dynamics simulations or more empirical models, but the truth is you would never actually capture exactly the situation on site. This is where data can help. We can actually fashion data-driven models. In this case, we use conditional variational autoencoders, and we try to have predictive models that accept as information just the mean wind speed and direction and information in this wind farm, and then they produce the prediction of the wind load in the individual wind turbines, as long as critical engineering quantities such as the wind deficit, which is manifestation of the effect of the wake on these individual turbines according to the angle of the wind, or even more useful for engineering calculations, the so-called damage equivalent load, which is basically the fatigue that is experienced by these turbines. And in all of the steps of this simulation, we didn't have to actually use physics. We used the sensed data and neural networks that worked on conditioning on the mean characteristics of the wind, which means that data could take us where models probably could not. But unfortunately, this is not always the case. In fact, in our group, what we maintain is that data itself is actually not enough. Instead, we know very well today that the use of data is very good for essential tasks, mostly having to do with the diagnosis of damage, but are not so informative when we try to go a bit further. So I'm going to show you a few instances of what you can do with data alone, and actually this is work where Simona Bogoevska from the university here was involved, where we use sensors deployed on wind turbines. We extract vibration-based information, typical structural health monitoring information, in other words, and we condition this information on the environment, the mean wind speed, direction, the acting loads that are gathered from SCADA information on these turbines. And what Simona helped us do, and then we have been following this pretty much ever since, is to build hierarchical models that can predict the response of a system based on its conditioned environment. And that's all very good. It's, again, mostly data-driven. There's some dynamics that is cast onto this framework. And what it means is that we can predict, we can fashion indicators that look at the deviation between what we measure and what we predict, and then we can have classifiers that can essentially characterize the response of the system as either pristine, everything is going well. We can issue alarms, so basically we have anomalous response for areas of the loads of the acting winds where we have confidently trained our model, so we know what's going on and we know that we're picking up an anomaly. Or we could have yellow alarms, which means that there is something going on with the system, but we're also picking up new information and new data, and so we need more inspection information to characterize what's going on. And this is fine. We can organize these maps and offer them to the engineers and operators in a red, amber, green alarm type of system, because oftentimes this is more appreciated than the details of the learning algorithm or the system identification algorithm that is in the back. But this essentially means that we restrict ourselves to the task of detection. One step further, we could show that if you take into account the distribution of sensors on a system, such as a bridge or a turbine, you can also achieve perhaps the task of localization, understanding where an anomaly or damage may exist. And this is something we have shown on a bridge. We have controllably damaged as a benchmark in Switzerland. We have ourselves implemented a few different characteristic damages, and we have deployed different acceleration and strain sensors on the bridge, showing that it is actually possible from the distribution of these sensors and from associated metrics to understand where damage is present onto the system and pick it up. All of these tasks are still, however, limited to the main effort of diagnosis, so understanding what the condition of a system is currently, but they lack insights into the prognosis or prognostic behavior of the system, which means where can it go or how far can it go next. And this is actually where data is known to suffer. The information that comes purely from data is usually not easy to interpret so that you can make future predictions. It lacks explainability and physics connotation, so you cannot necessarily link quantities that you measure to others that you're interested in and that you do not measure directly. And you can also not extrapolate, so it's very hard to say how will this evolve in the next years to come, which is typically needed for resilience assessment, which is also the topic of this meeting. Another issue where data is very weak is the fact that typically you only know what you measure. And if you have not covered the entire system, the danger is that you're basically viewing a very local image, which is quite misleading. It's not giving you the full information about how a structure can actually behave. And if you are only using data-driven approaches, then you're also not exploiting perhaps the biggest strength of what we have as engineers, which is the physics intuition and the explainability that it can offer. So this is where we argue that data is not enough, and the moment you want to go further away from understanding a structure as is or as monitored, if you wish to go to the tasks of prognosis, it's important to now bring in physics into the formulation. And of course, physics-based simulators are very heavily used by engineers, typically though for what we call digital twin prototypes, so basically systems as designed. And once they are designed and deployed, if you don't use those models in conjunction with data, it means that you're basically losing the strength in efficiently understanding and monitoring these systems. To the contrary, if we use a hybrid approach, which is what I would like to discuss here today, so if we fuse engineering models with data, then we can have digital twins that are actual interactive systems, closed-loop systems that can bring the best of both worlds. So this is what I will show you now, and I'll try to explain how models can be built to come into synergy with data. One application for doing this is a project we recently concluded. It's a large European project on data-driven seismic assessment. And here our task was to use these hybrid models for early warning systems. So we have data that are extracted from buildings prior to seismic events, joined with models so that we can have updated let's say, digital twins of the system behavior. And then once a seismic event occurs, we try to show how minimal information from monitored buildings can be used to fashion early warning systems at the city scale level. Actually, to do this, and this was work with Panos Martakis and Yves Roiland from our group, who are now leading the IRMOS technology startup exactly on this theme, we were collecting a number of information actually from buildings throughout Zurich, where it was important to also collect information beyond the mere linear behavior. That's why we collected information also through demolitions of buildings, giving us stronger loads and a possibility to build models that reflect different typologies of mostly masonry systems throughout Zurich, which we then used for updated and improved fragility curves and analysis for seismic prediction. But in this kind of a construct that I'm showing you here, the digital twin is sort of an updated model, and it's not what I would actually define strictly as a digital twin. In fact, what we're more interested in our group is what you would call a real-time digital twin. This means that you have a model that computes in real time as fast as data is attained, and usually our data are dynamics, type of information. So we need models that compute in fractions of a second. We also need models that can take into account varying environmental and operational conditions, distributed excitation, the fact that we have uncertainty in our collected data, and we need them to be living in a synergy with the actual operating system. There are a number of reasons why this is desired, not less of which is the control, hybrid monitoring applications, or hybrid testing applications. But more important for us is the so-called task of virtual sensing, which is essentially what I also refer to as trying to achieve everything, everywhere, all at once. And here's the description of the system. Assuming you have a structure that you're actually extracting information from in the form of sensors in some sparse and limited locations, these systems usually operate under unknown loads. In most cases, whether this is a bridge or a wind turbine, we cannot really collect exact information on the load that is acting on the system. But as engineers, we do have some sort of model, usually not calibrated, so the uncertain parameters are there. But the model structure or model form is also roughly there to describe our problem. And we would like to extract information about the unmeasured response of the system that is of interest to us, whether this is strain in hotspot locations or maximum deformations that you would like to check against specific thresholds. This is basically the task of virtual sensing. And ideally, we would like to do it in what we call the full field. So we would like to extract everything, the unknown information of the system and the response, everywhere in as many virtual sensing locations as feasible. And we would like to do it under the restrictions of the uncertainty and noise that is corrupting our data and our models, the fact that we have complex systems with limited observations and very large dimensionality, since we're talking about real structures, and we would like to do it in real time, which essentially means all at once. So this is the basic definition of the problem, and now I'll show you how we can achieve this. And the way in which we can achieve this is is by going beyond what your traditional structural mechanics or structural analysis tools could do for you. Of course, we are a structural analysis group, so we also work heavily on conventional theories for fracture, plasticity, and whatnot. But these do not make the cut. These kinds of theories will not allow you to compute in real time, but they're very useful because that's where we start from in order to produce these reduced order models. Now I'm showing you here one example of such a scheme where we have a full order engineering model reflecting a typical instance of a civil structure, which is a shear frame. It's a shear frame which is excited by earthquake, and it features nonlinear links that exhibit hysteretic behavior. These nonlinear links are governed by a Book-Wen model, in this case, hysteretic law. Of course, you can have any other assumption you wish for. The point here was to try and take such a system and reduce it so that it can compute fast enough for us to combine with data. And we want to do this by also parametrizing the different, let's say, properties that define the system, not only its geometry and the properties of the hysteresis, which are parameters for us, so they can change, and we want for different sets of these parameters to produce the response, but also for different types of excitation that characterize the earthquake, different temporal and spectral characteristics of earthquakes, which is also something that we can easily show can be done. So having these parameters, now we want to have a dynamic model. We basically want to have something that solves the dynamic problem as a time history, not as a rough static calculation, as a proper nonlinear dynamic time history, for different parameters of these systems and different inputs. And so we start from our traditional numerical or finite element simulations as civil engineers. We have a nonlinear finite element model in the back, which is where we start from. We generate a finite set of simulations from this model, and we use a projection type of approach, essentially a Galerkin type of approximation, which allows us to take the original multi-degree of freedom equation into a reduced order form that we can solve very, very fast. We do this by essentially using the so-called proper orthogonal decomposition tool. And what this means is that at the end of the day, for different sets of parameters, so different regions of my parametric space, different geometrical configurations of these buildings or different hysteretic properties or different loads, I can produce a very fast computing model, which is also sufficiently accurate. Now, there is one more aspect that is of importance for us and which we have brought into this simulation, which is the fact that we don't only produce predictions that are deterministic, but they're in fact probabilistic in nature. So not only can I produce the time history of the simulation, but I can also have some confidence as to what is the estimate that I'm yielding. And we do this by using a variational autoencoder. I won't go into the details of this, but here we are basically using machine learning to the benefit of physics and not blindly as a black box. And this is the main difference to other type of tasks. Now, what it means is that you have different parameters for the amplitude of your load or parameters for the main frequency content of an earthquake. You can produce time histories of the response of that building in real time, actually in fractions of seconds, which is faster than the real time than we would need. And you can do this by approximating very closely the original reference model. And you can even produce confidence intervals that give us some sort of approximation of the error in our assumptions when we build such a reduced order formulation. So now we have something that computes fast, is efficient, and can also quantify uncertainty. But what I have not yet shown you, since I'm arguing a hybrid framework or a digital twin, is how you can connect this with the data. And the way in which this is done in our group is by following a spectrum of different approaches, starting from the very left end of this graph, which is what you would call closer to a white box model. It's basically an approach where you assume your model is as close to perfect with a few margins of error. And then moving into more gray approaches where we start to allow some error into our formulation. So I'm going to start first from this left approach. And here, the main tool that allows us to merge models and data is what we call a Bayesian filtering approach. What it means is that you have a model of your system. It can be a reduced order model that, like I showed you, or your favorite finite element model. But it's basically something that describes the dynamics. And then you can combine this with the sparse data that you really have or are measuring from a monitored system. Accounting for some portion of uncertainty, some model error, or some noise in the data. But at the same time, remember that in this formulation, we also assume that the model is accurate, the model form is sufficient. And so you're trying to combine these two information together, and the best way to do this is using a Bayesian approach. Now, for those who do not know this kind of an approach, what it says is that, first of all, that you have to operate in basically two steps. In a first step, where you use your model to predict what would be the response of a dynamic system at the next point in time, starting from time 0 with an assumption, you can use a model to go to the next point in time. And of course, your model can be whatever type of model you prefer. And then in a second step, and this is really where the Bayesian logic kicks in, you have to check how close your prediction is to the simulation or the model, to the measured, to the actually measured data, the observations you collect from sensors. By checking the discrepancy between the two, you can correct your previous estimation and get an estimated, what we call a posterior, which is the best of both worlds, meaning the combination of models and data. So it's a sort of balance that you always try to achieve, but the key in this approach is that physics enters every part of the simulation because the models are entering these calculations explicitly. So this is how we solve this kind of a problem, and we have tried to do this for various applications, for understanding the response of the system in unmeasured locations, for predicting not only the response, but also the loads that are acting on a system, for understanding what are the parameters that are describing the model form, for doing all of this at the same time, which is also possible, even if it is a bit more difficult and requires specific measurements. And so there's all these schemes that, depending on your problem, you could actually use this Bayesian logic for. Now, I want to show you a bit on how this can be done on an example. So this is an example of a fuselage structure. It's also a structure taken from an aerospace application. And the fuselage is this thin shell where we assume that we have some few sensors here on the red locations typically in the form of strain or acceleration, and I would like to use these sensors to infer damage onto the shell, which is usually in the form of cracks, multiple cracks that could occur throughout the structure, and also to understand what is the response of the system in unmeasured locations. Now, to do this, I will use the process I showed you before with a few more tricks that we employed by using structural mechanics principles, and what you can see is basically the computation. It's a dynamics simulation of a cracked, thin shell curved structure, which is computed in real time, actually much faster than the video here is able to show this, and which is now ready to be coupled with data. So to couple it with data, I place it in the Bayesian filtering scheme that I showed before. It's a scheme that assumes that the input, the load to the system is not known. The parameters of the system, which are the locations of the crack and the orientation of the crack, are not known. And I'm running these parallel computations with the Bayesian logic that tries to approximate the sparse measurements that I have. So by doing this, I can actually converge. I can figure out also at the same time what is the location and identify, in a sense, the damage in my shell structure, because I can find the location of these cracks. Quite importantly, I can also, in a virtual sensing mode, understand or predict what is the response, the strain, or the displacement of the system in unmeasured locations. And I can do all of this in 0.12 seconds for a simulation that corresponds to 20 seconds of real time, and where the best computing finite element model, even with tricks and reductions, would take at least 22 seconds to compute. To show you one last thing, what I showed until now assumed that as engineers you have a pretty good computing model, but we all know this is not always the case. Usually our models can have an error, and this has to be accounted for. This is what we call model mismatch, and it is possible to also take this into account by moving a bit more down to this gray spectrum that I showed here, by assuming, therefore, that your models are also suffering from some sort of uncertainty and mismatch, and it's not just the parameters that are unknown, but also some vital terms that are missing to describe the behavior. These vital terms are often coming from damping assumptions, for instance, because we all know that damping is not very well described by our assumptions so far, and it always tends to give some discrepancy with respect to the system. So to tackle this, we have been using physics-enhanced learning, which means we have been coupling the ideas I showed you before with portions of neural network architecture, but in a way that always brings a synergy between physics and these machine learning tools. And this is work that is done in Singapore with our group there on physics-guided, physics-encoded, and physics-informed schemes. I won't go into the details of the differences of those, but for those interested, you can reach out to me after that for a discussion. Instead, I will show you how it works. So the first scheme that I mentioned was the physics-guided scheme, and here what we try to do is to fuse the portion of the models that we know are governing the behavior of a system, so the part of the physics we know, for example, the linear part, most usually, is what we're very good at as engineers, and then we couple this with a learning term, so we basically allow a neural network representation to learn the error between what we know and what really governs the system and is manifested in the measurements. So it's a superposition of these two, let's say, predictive models, but it's always here, there's always a part of the physics that's guiding the prediction, allowing us to deliver estimations that have a physical connotation and are not just black box estimates. This is shown here in this toy example using a pendulum. We claimed that we try to approximate the pendulum behavior using a linearized model. We used images and not time history data, which is the nice thing about these frameworks. It's not necessary that you use vibration, acceleration, or strain measurements. You can also use video or image data, which is also has become more easy to extract in these days. And so we show here that by using just acceleration information from this, or displacement, excuse me, video information from this system, we can also learn things that relate to the physics, such as the velocity, the angular velocity of this pendulum. You can only do this by fusing physics into the equation. If you try to do this using a pure black box learning approach, just a neural network, there is no reason why it should learn the angular velocity just because it does not know what that is. It just knows what it measures, essentially. So we took this idea and we put it onto a real problem, which for us is onboard monitoring, the deployment of sensors on vehicles or cars so that we can understand the behavior of the traversed infrastructure just by collecting vibration data from these vehicle systems. This is a project we have both in Switzerland with the Swiss Federal Railways and Singapore, where we do this dynamic mobile sensing platform. And you see Hara, who is working on this kind of a project. And so we used this framework that I showed you before to connect a physics-based model of the vehicle, which more or less we know, with a learning model of the rest of the system, which we don't know because we traverse different roads, different bridges, and we cannot claim to have models for all of these systems. And so by fusing the two, we can actually get a convergence. We can infer the quantity of interest, which in this case is the roughness of the road. It's one of the quantities we would like to offer so that as a quality indicator for the roadway system. And you see that the optimal mix, there is an optimal mixing of physics and machine learning to do that. And in fact, even though I'm forcing it here, this is something that's automatically done by the framework. I'm not going to show you some further applications. For those interested, we have verified these models on real civil structures with nonlinearities. We even showed how you can actually extract the hysteretic behavior of these nonlinear structures. We have done it on real data from actual buildings in the US that are monitored under earthquakes. We have shown how you can predict their response using these systems, or even how you can predict damage under real experiments for wind turbine blades. This is very important for us as validation, but it basically showed that we can now trust our predictive models, and the question is what to do next. And what to do next is to use this information to guide the operation and maintenance of these systems. And again, this is where we're lucky to work with the Swiss Federal Railways because they have offered us access to monitoring data. This means that we have been allowed to develop indicators of the condition of the tracks and of the ballast of the railways. We do this by using monitoring data from their trains, their diagnostic vehicles. The indicator, in this case, the so-called fractal value. So we use the evolution of this indicator over time, and we combine it with information on the costs that different repair actions of different gravity would have onto the system in terms of not only the monetary cost, but also the downtime, how long you have to close down a track so that you can perform operations. And by solving essentially an optimization problem, but by a problem that assumes uncertainty in the observations, in the sensor data that we collect, we're able to give them a strategy, a policy, or a plan on how to best spend their budget for repair and intervention in the next horizon that they are interested in. And this is usually 5-year horizon steps for the Swiss Federal Railways. This is done by using a partially observable Markov decision process, and it's basically something that allows us to fuse uncertain data with information on decision. So this concludes the talk and a bit of the vision that I wanted to discuss, which essentially is this vision of augmented twins in the sense of building models that are data and physics informed and that can be delivered to the experts and actually bring them in the loop for efficient operation and maintenance, which is the way in which we imagine that actual civil and general engineered systems should be operated on. Thank you very much, and I look forward to talking.
Professor Hadji, thank you for your presentation. It was quite inspiring to hear you today. Now I would like to open the floor for questions. Are there any questions from the audience? Yeah.
Thank you for your presentation. Monitoring is very important for our structures. Especially was impressive your second part of the presentations about interpretation of results, modeling. I was a little bit late. How you collect data from the sensors? By cables or by wireless?
Yeah. So this is a good question. I started by saying there are many ways to collect data nowadays. So we use all of them. So we actually use wireless sensors, wired sensors where this is easier, For example, for the monitoring during demolition, it turned out easier for us to just have an octopus setup with wires and cables that were easy to deploy and synchronize in a single unit, and it seems surprising, but it was with such low-cost sensors that we could afford to even lose them during demolition, for example. So that was fine there. But you can imagine that for other cases, you want wireless sensors, or, for example, in what I showed with trains and cars, you have sensors that are moving, so they can be wireless or wired, depending on the power source that you have.
Because the quality of the data on wireless sensors about some parameters like vibration, frequency parameters, are they with good quality or not? Because time sampling is...
In wireless sensing specifically, you have to solve specific issues like synchronization to get good quality data. We have worked also on such approaches, but the way in which this can be made to operate well is by, at the same time, compressing the data, because you cannot afford to stream huge packets of data just on wireless. So there are several solutions for this, you're right, and they're necessary. Today, it has become increasingly easier to cooperate with telecommunication companies, which is also something we do, for processing part of this information and sending it on the cloud, where it is more efficient to do a lot of these tasks, in fact. And we also forget about saving the data, which used to be a huge bottleneck. But I have to say, my point is that wherever this information comes from, and I think in the future it will become more and more, there will be more and more diverse ways to get this information, you always have to translate them in a way that's interpretable. So it's not just about collecting as much as you can. You still have to find a way to link it in a way that makes sense, which is where a model would be useful.
Okay, thank you very much.
Are there any other questions?
Thank you for this presentation, very inspiring indeed. Also, a short question, it's more a background. There was a time when fuzzy logics were a big hype, and I saw your concepts of evaluation are classical concepts in a very, very updated modern form. Markov chain with one-step memory and these things, Bayesian filtering. Do you think the time of fuzzy logics is over, or did it ever work properly?
Yeah. Fuzzy logic was actually a very good way to take uncertainty into account. I don't think its time is over. I think that this is the point. You have to take such schemes into account. Now, you saw me insisting on the Bayesian filtering framework because it's something I have been working on since 2006, really, and it's very convenient, not so much because of the equations it offers, but because it's flexible. It can be made to account for uncertainty on any part, whether it's from the data or the model. It can account for linear or nonlinear logic. It can account for model mismatch of portion of the, just because of the way in which you're free to then formulate this posterior probability, let's say. But of course, you can also choose other ways to take that uncertainty into account. In fact, we also partially do this using this variational logic, which is an alternative to the Bayesian logic. You saw that I referred in a few instances of my presentation to variational autoencoders. There, the logic is similar, but actually not identical. We try to minimize a likelihood function, the so-called elbow, or maximize it. But again, the idea is to balance what you can see in the data and what is the uncertainty that causes a discrepancy between your prediction and the data. So the fuzzy logic era is not over. It's just probably another way to look into things. And I would welcome any such approach that looks into uncertainty.
Okay, thank you. Are there any more questions, or we can... Okay, there are no more questions, so we have one more thing from the organizer. One small acknowledgement of your presence here and your talk.
Well, next part of this session is reserved for sponsor presentation. First is Knauf Company. This is the silver sponsor of this symposium.
Добар ден на сите, јас сум Зотовски Блажан, архитект меѓу градежниците денеска. Прво да му честитам на организаторот за преубавиот собир и за безпрекорната организација и да го предупредам дека за 2025 година доста го дигна критериумот. Уште кога почнав да работам презентацијава пред цирка месец дена, ми беше интересно колку современ збор е избран за името на настанов, или resilient building, значи не се resistant, не се energy efficient, и околу 15 на години сум во градежништво, ми стана интересно колку пред 10 години бевме задоволни со многу поедноставни својства на објектите. Зборевме за функција, како архитектите, зборевме за енергетска ефикасност, зборевме за стандардна противпожарна заштита, стандардна звучна изолација, зборевме за економични конструкции и бевме многу среќни ако објектот има и евентуална некаква повишена енергетска ефикасност. Во последниве години сменивме парадигмата на размислување и веќе ни станува потешко, имаме повеќе критериуми за исполнување. Збориме за одржливост, колку и да е тоа широк збор, збориме за повишени човечки потреби. Ако зборевме за нормална звучна изолација и противпожарност пред 10 години, сега збориме за потреба од повисока звучна изолација, повисок комфорт, повеќе кислород во домовите. Така да зборуваме за многу понапредни теми. Не збориме за отпорност на објекти, збориме за позитивно однесување во случај на земјотрес. Ова, се што го гледате, не е некоја новина за градежниците, затоа што градежниците овој пат го трасираат долги години, со нивното искуство и со вакви трудови, какви што ги гледаме вие 2 дена. Ви благодарам за тоа. И КНАУФ е тука, освен со нивните со своите системи, тие потреби да ги промовира и преку дигитализацијата. Не сте слайд за дигитализацијата, само ќе кажам дека овој месец лансиравме еден плагин за Revit, односно за BIM, кој што се вика Planner Suite и кој што е олицетворение на мултидисциплинарност на градежништвото, ке не соедини градежници, архитекти и други инженери. КНАУФ во Македонија е 30 години следната година, а во светски рамки влеговме во последната декада пред одбележувањето на 1 век од постоењето на компанијата, и тоа е еден период кога сакаме да подсетиме на некои веќе познати својства на нашите системи и да си поставиме нови предизвици. Она што го знаеме во Македонија, од она што се цитира во дефиницијата за resilient buildings, е дека гипсот е 100% природен материјал, дека во него отсуствуваат сите штетни материи кои што може да се појават во градежни материјали, дека е 100% рециклабилен, а во светски рамки и веќе голем дел од гипсот и од КНАУФ материјалите се произведуваат од рециклирани материјали, и оно што е најголема гордост дека сме секаде присутни и дека производството секогаш ни е локално и нашите објекти ги работат локални изведувачи. Оно што во станоградбата особено го направивме во последниве декади е покажавме дека КНАУФ системите секогаш се потесни, полесни, со повисока звучна изолација, со побрзо време на инсталација и со многу повисока енергетска ефикасност. Значи, тоа е веќе многу познато. Оно што е интересно исто ова се податоци што влегуваат во проектите. Оно што е интересно за овој собир се цитати од едно издание кој што се вика КНАУФ Drywall and Seismic Buildings, кој што е достапно на нашата интернет страна. Тоа е една кратко резюме на однесувањето на објектите исполнети со сувомонтажни системи наспроти традиционалната зидарија. Нема да кажам ништо за градежниците ново, ако повторам дека КНАУФ системите за сува градба, односно технологијата за сувомонтажни преградни зидови, не ја вкрутуваат зидаријата, односно не ја вкрутува конструкцијата како што го прават тоа по старите технологии. Нормално дека тоа дава малце повеќе простор, малце поширока, појака дуктилност на објектот и многу помала штета при евентуален земјотрес. Намалената маса, нормално само масата кога ја споредуваме, потребата на КНАУФ системите наспроти оние традиционални системи, значи намалување на масата, на онаа некорисна маса на објектот до некогаш и до 80%. Обично околу 65 со нормални параметри на звучна изолација и противпожарна заштита, кај посовремените објекти, каде што се бара повисока звучна изолација, а панданот на зидовите на КНАУФ би била некаква зидарија од 70-80 см, таа олеснување може да иде и до високи 83%. Ова е еден многу интересен извадок од една симулација на петкатница, тоа беше петкатницата која што видовте во претходниот слайд, и параметри кои што вие како градежни инженери секако многу поубаво ги разбирате од нас архитектите. Особено ќе ставам акцент на последните цифри, каде што во споредба на сеизмичкото оптоварување што конструкцијата го трпи при исполна од сувомонтажни системи, наспроти constraint masonry, што би рекла професорката со стручен речник вчера, се гледа дека товарите се скоро 3 пати, односно напрегањата се скоро 3 пати помали. Дополнително нема да биде sustainable, нема да биде resilient, ако не збориме и за евентуалните штети, нормално, полесни зидови, полесни за санација, дури и при поголеми оштетувања. Значи, многу полесно се санираат, санирањето е многу поекономично, па дури ако се случи најлошото, дури при колапс на објектите, трагањето и спасувањето на преживаните е многу полесно. Она што традицијата што го налага е малце по, речам, да не сгрешам збор, по опасен начин на оштетување на објектите. Немаме само слики, оваа година одбележавме 60 години од земјотросот во Скопје, еден темен датум, меѓутоа лекциите се извлечени и имав еден убава организација со колегите инженери од ИЗИС. Направивме една убава мустра од 2 кналв преградни зида, соодветен спуштен плафон и подигнат под. Во првите неколку, имавме 3-4 пригоди да ја тестираме мустрата, во првите неколку користевме вистински земјотресот од Црногорски Петровац, 1979 година, околу 6,3 на европска сеизмичка скала. И на наш предизвик, прифатен од инженерите од ИЗИС, вториот на последниот термин од тестирање, 25 јули, и после кратка пресметка, почнавме применивме слайд, како го викаат, значи на точната резонантна фреквенција на зидот. Беше негде околу 4 Хц. Знаете што се случува со градежен елемент кој ќе се постави на резонантна фреквенција. Што е интересно за мустрава, како практичари, морам да ви кажам дека мустрата ја правеа локални мајстори од Скопје и иако им стоев над глава додека се работи, ги оставив целата мустра да ја направат со секојдневен квалитет како што и градиме сите објекти во Македонија. Немаше, народски кажано, штимање на мустрата и покрај резонантната фреквенција единствено оштетување што беше видливо нормално на внатрешниот агол помеѓу овие два зида, нормално овдека беше во бочна насока земјотресот, овде беше во паралелна, тука нормално испука спојот кој што по препорака беше направен, затворен со акрилен силикон и нормално декоративните лајсни кои што ги држаа неколку капки монтажно лепило, тоа беше единствената штета. Така да ова е една убава порака да се применуваат искуствата кои што ваквите собери ги промовираат и да се гледаме само за убави работи. Благодарам многу.
Следната презентација ни е повторно од компанија, спонзор на овој наш собир денеска, тоа е компанијата Масон. Повелите.
Добар ден, јас сум Никола Стрезовски од Масон инженеринг, исто архитект како и Блажен, што на ваше место и јас би го сватил како провокација, затоа што Масон втор пат поред испраќа архитект на ДГКМ. Денес сакавме побара од нас малку позабавна презентација да биде, па ќе се обидам да не затупам. Живееме во 2023 година, каде што благодарение на интернет и социјалните мрежи светот е поделен. Во смисла на секој може да каже што сака и има тоа негово мислење, има пристап стигнува до многу луѓе, така што се добива некој впечаток на поделеност на светот. Ако ја прашаме вештачка интелигенција како изгледа, например, на овој собир, типичен архитект и типичен градежен инженер, тоа некоја ваква представа ни дава, како две спротивставени, поделени страни, типична жена архитект, типична жена градежен инженер, тука веќе помала е разликата. И како изгледало секогаш борбата меѓу градежните инженери и архитектите, илустрира на некој начин ова мим. И сега, за да секогаш се обидуваме луѓето да ги ставиме во нека категорија, ти припаѓаш на ово или на оној табор, тука би го цитирал Ле Корбузие, еден од најголемите архитекти на сите времиња, кој што во книгата Конвистинската архитектура вика да ги послушаме американските инженери. Ние од Масон, како компанија, сега не ставате во кош. Значи, добро, тие се за американците. Но вториот дел од цитатот е: но да се чуваме од американските архитекти, што одма после тоа следува дека значи може да се во другата категорија, но тука сакав да дојдам до целта на она што сакав да го кажам за денес е: го послушавме Ле Корбузие, ги послушавме американските инженери кои што градат во челик. И ова е обид за првата челична стамбена зграда во Македонија, која што ја проектиравме ние, а екипата која што ја го правеа проектот за конструкција е катедрата на професор Денис Поповски, Миле Партиков, Никола Нисев. И заедно, тоа што не обединува дополнително е тоа што овој проект го работиме заедно во BIM, конкретно во софтверот Revit. И ова е архитектонскиот модел, како изгледа комплетниот модел. Тука се сите прозорите, тука се оние сите основи архитектонски што ги даваме како оно што треба да се прават во општина, квадратури, табели, тука се архитектонските детали, сиот тој процес. Дополнително ова е конструкцијата, исто сработена во Revit, која што ние даваме предлог, тие на тоа се надоврзуваат, продолжуваат да го работат. Ќе го видите нивото на кој е изработен проектот и нивото на деталност. Ова е челичниот дел, ова е арматурата. Ова е нешто што јас не го разбирам, ама ми делува многу забавно. И исто и ова е сработено од катедрата на професорот Денис, конкретно од Никола Нисев, како се гради конструкцијата, конструктивните елементи, градежните конструктивни елементи, столови, греди, секундарни носачи, плочи, на кои што после се надоврзуваат архитектонските елементи. Зградата треба да ја почнеме наредниве денови, ќе биде позади Народна банка од спротивната страна на Ману. На кеот на Вадар и ова се некои рендери, тоа сватив дека колку повеќе се дружам со градежни инженери, толку помалку време обрнувам на рендерите, така што ова е некој ниво кое што треба да го подобриме. И се надевам дека ќе имаме успешни проекти до крај. Благодарам.
And the last presentation in this section is by WBE company, Facade Engineering. Do we have present? Yes. Okay.
Добро. А сега се пуштаме презентацијата. Почитувани присутни, јас сум Елена. Со мене денес и Емилија, ние сме представници на компанијата Willems Facade Building and Engineering. Прво ќе започнем со компанијата, значи таа се занимава со проектирање на алуминиумски и челични конструкции, како и изработка на 3D модели и работилничка документација за фасадни конструкции. Компанијата, односно канцелариите во Скопје се отворени во 2019. Започнаа со еден инженер, меѓутоа денес тимот има околу 11 градежни инженери. Исто така има представништво во Белгија, односно канцеларии во Гент, каде што има 4 градежни инженери и останатите се технички цртачи или лица обучени за цртање. Од фасадно инженерство ние се занимаваме со консултантство, односно со проектирање на системи, како што, например, се фасадни ѕидови од стакло, односно изработуваме модели со 1D елементи од алуминиумски профили, во кои ги пресметуваме со зададените товари, при што, ако не ја задоволуваат носивоста, даваме и совети за појачување на профилите, односно на системите. Исто така, изработуваме и пресметка на стакло во софтвери како што се Vitralis и Mepla. Освен тоа, пресметуваме и фасадни вентилирани фасади, како што се системи од хоризонтални и вертикални елементи. Во принцип, првично пристапуваме со системи од 2D плочести елементи, кои најчесто се од алуминиум, меѓутоа можат да бидат и од инокс. Во случај, ако не може да се направи доволно детална студија со 1D елементи, тоаш пристапуваме со моделирање во 2D плочести елементи, при што се земаат карактеристиките на течење на материјалите во предвид и така се пресметува носивоста. На сликата е представен еден објект кој се наоѓа моментално во Антверп и мислам дека е награден за најдобра фасада. Освен тоа, изработуваме и модели за касетни системи. Касетните системи најчесто се од алуминиум, при што се зема во обзир дека постојат и хаз зони кога се работи за заварени врски, така што во моделите ги внесуваме карактеристиките со намалени технички својства на хаз зоните. Освен касетните системи, ние ги пресметуваме и врските, односно пресметка на завртки, на штрафови, на фаблокс, попнитни и слично. На едната слика е представен објект, односно икон Белвал, кој се наоѓа во Луксембург и представува објект канцеларии од отворен тип, нешто слично како ГТЦ, а на другата слика е представен објект Симак, Симак е лоциран во Белгија, се работи повторно за алуминиумски касатни системи, но тие се перфорирани, односно олеснети системи. За таа цел ние првично влегуваме со студија за пресметка на една замислителна дебелина на алуминиумските касети, при што кога ќе добиеме таа дебелина на плочи, потоа влегуваме во главниот модел. Најчесто за фасадните касетни системи ние вклучуваме и геометриската нелинеарност со цел да може да се искористат придобивките од мембранско однесување на касетите. Освен фасадни елементи, пресметуваме и помали челични конструкции, како што се секундарни челични конструкции, огради, платформи, настрешници и слично. Исто пресметуваме и анкерни системи, без разлика дали се работи за анкери како навојни вретена или пак анкери според некој производител, како што се Fisher, Wurth и слично. По потреба за некои проекти направиме и студии за стабилност, како и пресметка на геометриска нелинеарност на системите. Пресметуваме и врски во идеја статика, при што се земаат во предвид и крутостите на врските. Повели.
Здраво. Јас ќе продолжам со тоа што ќе кажам каде се лоцирани нашите клиенти, поточно нашите проекти, па така ние работиме за европски пазар, тоест Холандија, Луксембург и во главно за Белгија, како што можете да видите на мапите горе. Значи ние работиме во софтвери и со кодови, конкретно работиме со SCIA Engineering. Значи во SCIA ние ги моделираме и ги контролираме конструкциите. Потоа, по потреба во идеја статика ги моделираме и ги проверуваме исто така врските, или HiCAD софтверот го користиме. HiCAD ние за моделирање и цртање на 3D цртежи и исто така за изработка на технички цртежи. Исто така, како што кажа мојата колешка, значи пресметуваме и стакло, тоест за пресметка на стакло ги користиме софтверите Vitralis и Mipla. Ние морам да напоменам дека работиме значи со еврокодовите, но бидејќи работиме за европски пазар, тоест конкретно за некои држави, исто така ги користиме и нивните стандарди, нивните анекси, исто така го користиме анексот WTCB, кој што е анекс за секундарни конструкции, исто така и за примарни, стандарди за огради и слично. Ние како вработени до сега сме биле на неколку обуки, па така фирмата нас ни нуди обуки за идеја статика, тоест конкретно идеја статика кампусот, или пак за анализа на стабилност на пластични зглобови. Исто така ние имаме и придобивки од ова, така да сме членови, да речем, на Спортмастер. Исто така имаме можности за посета на јазични училишта, тоест учиме холандски и француски, затоа што нели работиме за Белгија најчесто. Одржуваме и тимбилдинзи, сето тоа организирано преку Boost Factor, каде што имаме тренинзи за лидершип и слично. Фирмата исто така вложува и во софтвери, SimScale и Grasshopper конкретно. SimScale го користиме за динамичка анализа на ветар и тоа на некои покомплексни објекти, некои покомплексни конструкции, каде што можеме попрецизно да ги одредиме зоните на ветар, исто така како што го спомнав и Grasshopper, каде што имаме некое параметриско моделирање. Па така, јас ќе завршам со тоа што ќе кажам зашто сме ние денес овде дојдени. Така, ако сте заинтересирани за WVNA, за нашата фирма, можете слободно да не контактирате на имејлот долу кај Елена или пак во фоајето имаме штанд ако имате неколку прашања. Хвала.
Since we are way behind our schedule, I would like to introduce and invite our next presenter and speaker, Professor Predrag Popović. He will give a lecture today about the assessment
Стави ovo da se vidi, a onda...
and rehabilitation of collapsed fire-damaged concrete structures. Professor Popovic, the floor is yours.
Thank you for allowing me to make this presentation. I will talk about one particular project about collapse due to the fire and how we dealt with that particular issue. And I'm not going to talk that much about repairing concrete structures due to the fires. Many of you know more than I ever will about it, but I want to present to you issue that we had to deal with, how to rescue the whole building, preventing global collapse of the whole structure, and what we did to evaluate that remaining building and save it. The fire occurred on January 5th, many, many years ago, 40 years ago, in Chicago. It was a minus 20 centigrade. And the photograph was taken by one of our people on Saturday who was evaluating another facade. I received a call from the developer who was a contractor at home asking me to come down to the building, and I took myself many of those photographs afterwards while they were trying to extinguish the fire. What happened? There was a 25-story building under the construction, and on the 13th floor of the building under the construction, let's go back. What you see here, you see the fire that started at the wood formwork because one of the heaters exploded. The heater that was heating to keep the temperature down high in order to cure the concrete. In those days, there used to be a cycle of 1 week per floor. So I came down and I took the photographs while the firefighters were trying to extinguish the fire. And the way the construction was done at that time, and even today, is that there would be formwork, wood formwork, to support the forms before the concrete is poured. After concrete is cured, then it's moved up to the next one. And there would be formwork that would be, and shoring that would be shared between 2 or 3 floors. And the floor below would be only 1 week old. Here is what happened. 1 day old concrete that is not post-tension yet, it's supposed to be post-tension, had collapsed because the formwork caught on fire. You can see how interesting the situation is. You can see that large slabs of concrete are being hung from the tops of the columns with the cables that are not tensioned yet. So that concrete had no strength whatsoever. And it was loading the floor below, but fortunately not the total load went on it, but it was partial load because it was hung from the top of those columns. You can see the cables, how tight they are from the tops of the columns, and you can shear reinforcing that was placed on the top. What we took here didn't happen immediately because everybody was afraid to step on the top of the 13th floor. So we had a crane, construction crane that I used, that they brought me up there, and I had to decide what is safe for me and other people to go to it. You can see the damage on the columns. You can see the high-rise buildings there. In other photographs, you can see the huge slabs of concrete. To the right, you see the stair towers that these slabs are being hung from. It is obvious that there is a tremendous force in these cables that are holding the concrete slabs. Otherwise, they would have gone down on the floor below and would have collapsed the whole building. But the key that saved the building was, you can see there is a formwork below, because they would do 3 floors at a time, and they would take the shoring from the lowest floor, move it up to the top floor to pour the next slab. Therefore, the load of the newly poured concrete slab is being shared with 2 floors of that were already 1 week or 2 week old below. Underneath, there were cracks, and these shores that were about 10 centimeters by 10 centimeters, that was a standard 4 by 4 inch in US, reshoring and shoring that is being used, was holding the stuff. In order to start investigation and see what to do, there is a construction crane that is in place there that are used, and they pick me up from the ground, and we would go on the top of the building to investigate and see, is it safe to go down to it, and what is the situation and what could be done. There was also another crane for material and personnel that was exposed to fire. I don't know how many of you know, but there is a way to evaluate the temperature to which steel was exposed and see, is it safe. Here is my colleague, steel expert, who was coming, and there is a way based on the paint. You can see at the paint how much was the temperature of that steel during the fire. And it was safe to use that crane to bring people and equipment. This fellow here with a hard hat, white hat, that's me, many years ago. You can see what we've seen on the top. We have seen some funny shapes on the tops of the columns, free-formed hanging concrete shapes. But from the top from the crane, this is what we were able to see. We see the hung slabs on the sides, and it was only half of the 13th floor that was poured on the left. The right one, they had only formwork, there was no concrete there. And this is the stair tower in the middle. Another view, overall view, you can see all these slabs on the left. There is one thing I want you to pay attention on the left. Along the edge of the building, the pieces of concrete were hung as a necklace, called Giordani, on the side of the building and were ready to fall down to the building below. So the issue was, what do we do about these pieces of concrete? How do we bring them in without collapsing them and damaging the buildings below? This is another better view. You can see how many of them are along the edges. So being an engineer and being a much younger engineer, I thought I can solve everything by doing systematically things. So I had a plan that I mark up each piece of this necklace, and I said, well, I'm going to move this one and that one, which really is not exactly how it worked. In order to prevent them sliding down while we were going to bring them in, we had built some hooks based using whatever steel angles they had there. We picked them up with a crane and attached them to the ends of these hanging pieces on the side of the building. Here is how we attached them. And then we said we are going to do that at night, that we evacuate the building below, plus we did not want people to know what's happening. We didn't want any panic. And you can see each piece marked, and then we had these hooks there. Underneath, we put some wood grillages to facilitate sliding these slabs inward inside the building. Everything is ready there, but what we had decided to do, we were going to each piece individually wrap in steel cables and then attach those cables with steel chains to the inside columns to the building. Here is trying to attach all of these things. This is how they look. And then we would run the chains with the come-alongs, and we would attach them to the interior columns at the bottom of them. And the idea was that we were going simultaneously to bring them in slowly so that we prevent them falling down on the building below. This is the night that we were going to do this stuff. These are the photographs I took. And this is me with a white hat there, directing the workers what to do. And then we start moving this stuff in. Well, it's not that simple because it was all hung on the side, on the building at the edge columns. And therefore, if you move one of them in, it is like a necklace. You would move the others away. So it had to be done simultaneously, carefully, that as you move them in, that you will have to cut the cables so you can lower them down. But if you cut the cables here, you would damage the other ones. So it had to be done very slowly and simultaneously. We start bringing them inside the roof of the building at that point. And this is what we have done by the end of the night. We were able to bring all the slabs that were hanging on the side or big inside. Next day, we will have and cut those slabs, chip them down, and try to take them and remove them and evacuate them from the building. Break some of the concrete pieces that were hung there. Here is the top of the damaged slab on the 12th floor. When we remove all this other debris, you can see the damaged columns, overall view of the area with a stair tower. Then they had to cut the pieces of concrete that were hanging from the edge of the stair tower, and the stair tower was damaged as well. It was fairly simple. Columns that were damaged, we just cut them down. We would remove them, and we were going to rebuild them. Some of those that were not exposed, there was no concrete there, it was only the formwork, they just looked bad, but they were fine. They had just charred, we took samples and so on, and then they start removing the damaged columns up to the splice, which was there, and start removing them there. Some of them were fine, and some of them that was not concrete slab there, they were just superficially damaged near the top. We did have to prove that is all okay. There was an issue, what do we do with a post-tension concrete slab that was 1 week old below? What happened to the cables because of the temperature of the formwork that was on fire? Because there is a tremendous loss of strength in the post-tension cables if they're exposed to the fire. So how are we going to determine what is the remaining force in those cables? Is it sufficient? So we had to go at the edge. Fortunately, there were anchors were still there, and cables were still about 10, 15 centimeters outside. So we were able to pick them up, put a hydraulic jack on them, and pull. And we were able also to measure both displacements, and we placed something that would make a noise when we unseat those cables and seat them back. And we did that many of them around the perimeter of the building, and it was fine, which makes sense because the fire load in any fire goes up. So there is not that much damage on the floor below, but it had to be done. Now, this is the damage of those walls that were remaining for the stair tower. So the question is, what do we do? We said, we'll do nothing, continue with the construction, because it was a fast-paced, expensive building that had to be built. And they continue building it, and we said, we'll fix this afterwards. And after the building was completed, frame, the repair would include sandblasting and removing damaged concrete, chipping it, and what you see the reinforcing here, there is no corrosion, so you do not chip around it, but you just sandblast it, remove all the bad concrete, and by the way, building is already done. That was removed, and then we decided we are going to add another 4 inches, 10 centimeters of the wall. You should not do less than that because it's going to crack. Here's the formwork, and then concrete with a super plasticizer was poured from above. And this is how the thing looks like after the forms were stripped. And then what to do with the concrete on the top of the 12th floor. It was a superficial damage. So basically we just said we are going to sandblast, put epoxy grout. I don't like using epoxy grouts because they have a huge variation in temperature and shrinkage. However, this will be all enclosed and it will be under the carpet, so it will be stable temperature. And that's how it was done. That was done in 1981. That was done 42 years ago, and building is still standing, and it was a very successful project. Thank you very much. Any questions,
Professor
please?
Popovic, since we are time limited, I propose that we postpone the questions during the lunch break.
Okay.
So thank you once again.
Thank you.
Authors of the next presentations are Professor Boško Stevanović, Ivan Glišević, Dragoljub Todorović, and the topic is Palace of the Golubac Fortress.
Poštovane koleginice i kolege, Golubačka tvrđava se nalazi na ulasku u Đerdapsku klisuru i ona je, nema tačnih podataka kad je nastala i ko je napravio, ali otprilike neki pisani podaci počinju negdje, datira iz 1335. godine. Ona je vrlo značajna zato što Đerdapska klisura počinje na tom mestu i, da tako kažem, vlasnici ove tvrđave su bili i Rimljani, i Turci, i Avari, i Srbi. Preko puta ove tvrđave, sa rumunske strane, nalazi se takođe jedna tvrđava. Inače, Dunav je pre ulaska u Đerdapsku klisuru širok negde 6,5 kilometra. I ova tvrđava ima značajne strateške, važan položaj. Inače, tvrđava se sastoji od ovih 9 kula. Se vidi ovo ovde? Aha, ok. Pa dobro. Molim? A ovde ćemo poenter. Da, vrati mi nazad. Sastoji se od 9 kula. Ovaj poenter nešto mnogo. I ove palate koja se nalazi ovde. Može to mišem da se... Može, mišem. Kako se dešava? Zašto ne može mišem? gimnaziju. Znači, sastoji se od 9 kula i ove palate koje je označena slovom P ovde, ovaj poenter mnogo brzo prolazi, pa ne mogu baš dobro da ga... Evo je palata. Inače, pre rekonstrukcije ove tvrđave, put je prolazio kroz tvrđavu, bio je i neki tunel i ona je prilično bila urušena. Radovi na sanaciji ove tvrđave, na rekonstrukciji i revitalizaciji počeli su negde 2011. godine, a mi smo se uključili 2015. Kad kažem mi, mislim na kolegu Glišovića i mene sa Građevinskog fakulteta iz Beograda i kolegu Todorovića iz Republičkog zavoda za zaštitu spomenika kulture, kada je prethodna projektantska ekipa, da tako kažem, izašla iz projekta. Inače, rekonstrukcijom su izvršena rekonstrukcija svih kula, bedema i palate i ono što piše da je ovde formalno završena rekonstrukcija 2019. godine, to je zato što je tada prestalo finansiranje iz Evropske unije, a inače i dan danas se još neki radovi izvode na tvrđavi. Ovde vidite neke slajdove, snimke sa izvođenja radova. Tunel koji je išao kroz tvrđavu je pomeren. Vidite ovde na levoj strani radove na izvođenju tunela i dole tunel koji je završio, neke radove na kulama i na bedemima. A inače, danas još uvek se izvode neki radovi. Sad, znači, još uvek, ako mogu sad ovo da ispoentiram, bit će dobro, ako ne mogu. Ovde vidite arheološki park, ovo sa desne strane, ispred tvrđave, gde se izvode još uvek radovi istraživanja. Ovo dole desno vidite da su otkrivene peći za pravljanje kreča iz rimskog perioda i u toku je sada rekonstrukcija tih peći i pravit ćemo neke nastavničice da ih pokrijemo da ostanu za posetioce vidljive. A ovde sa leve strane postoji hamam iz turskog perioda i postoji rimska kuća koje su samo pokrivene i zaštićene da ne propadaju, ali ćemo njihovu rekonstrukciju nastaviti u narednom periodu kad budemo imali, odnosno kada budu imali para. Inače, evo tvrđava pre i posle rekonstrukcije izgleda nekako ovako. Zanimljivo je da godišnje tvrđavu poseti negde oko 150.000 posetilaca. Kada to podelimo sa 365 dana, odbijemo ponedeljak kad ne rade, to je otprilike oko 500 posetilaca dnevno, znači nešto kao ovaj naš skup ovde svakog dana prođe kroz Golubačku tvrđavu. Inače, što se same palate tiče, ovde vidite neke ostatke te palate, praktično samo jedan zid je ostao, ona se sastojala od podruma, prizemlja i sprata. Podrum, kada je urađena ova brana na Đerdapu, je potopljen i vidite ovde sa 10 strana ostali su samo neki temelji. Sama rekonstrukcija te palate sastojala se iz dva dela. Prvi deo je bio da rekonstruišemo i nekako uradimo temelje te palate, a drugi deo se odnosio na gornji deo, odnosno na prizemlje i sprat, da tako kažem. Što se samih temelja tiče, tu je bilo raznih varijanti da se naprave neki zagati, da se uradi ovo, da se uradi ovo, da se obnovi i onda smo se odlučili da to uradimo, odnosno da tlo saniramo metodom takozvanog jet groutinga. Jet grouting podrazumeva da se u tlo ubacuje, ajde da kažem, neko cementno mleko koje tlo poboljšava, pojačava i prave se takozvane kolone. Ovde na ovoj levoj skici vidite kolone ispod samog zida koje su išle pod uglom, a sa desne strane su kolone bile vertikalne. Na taj način smo dobili, evo vidite, u gornjem delu radove, na izvođenju jet groutinga, a ovde vidite te kolone. Znači nešto kao šipovi, ali nisu šipovi, nego je to zemlja praktično ojačana cementnim mlekom. Preko toga smo naravno uradili jednu betonsku ploču i nastavili sa radovima na gornjem delu palate. Gornji deo palate je predviđen, odnosno urađen iz dva, da tako kažem, segmenta. Levi segment koji vidite u ovom levom slajdu, gde je ostao jedan zid, Tu smo uradili klasičnu drvenu krovnu konstrukciju, a na ovom desnom delu, gde nije postojalo ništa, tu smo uradili konstrukciju od potpuno novu, od lepljenog, lameliranog drveta. I ovde vidite neke radove u toku podizanja ove drvene konstrukcije. Bilo je to naravno betonski zidovi, sve ono što podrazumeva za ovu takvu konstrukciju. Lepljeno lamelirano drvo treba da radi firma Piramide iz Sremske Mitrovice, međutim, nisu se naravno dogovorili oko para, pa je konstrukcija uvezena iz Austrije. Na ovom srednjem slajdu vidite pogled prema Dunavu. To je fasada koja je urađena u staklu, potpuno u staklu, sa aluminijumskom podkonstrukcijom. I na ovaj levi deo gde je urađena klasična drvena krovna konstrukcija, a kao što sam rekao, na desnom delu je lepljena lamelirana konstrukcija. Sama konstrukcija nije nešto sa aspekta tehnike, proračuna, ništa posebno. Bilo je malo problema oko ove galerije koju vidite na levom delu ovog slajda, jer arhitekta kolega Todorović nije dozvolio da imamo nikakve stubove, pa smo morali da je kačimo o krovnu konstrukciju, tu je bilo malo problema, a inače je sve to završeno kako treba. Ništa posebno nije, kao što sam malo pre rekao, konstrukcija palate, međutim, ovo predstavlja jednu prekretnicu u projektovanju istorijskih spomenika. Zašto prekretnica? Pa, obično istoričari, odnosno ovi arhitekte koji se bave i konzervatori, uvek teže da naprave nešto kao što je bilo. Međutim, ovo je prvi put da smo uradili nešto potpuno novo, znači nešto što, da tako kažem, sa jedne strane može da bode oči kad pogledate u samu tvrđavu koja je sva od kamena i tako dalje, ovo je nešto novo, staklo, ali kažem da je sama konstrukcija se relativno dobro uklopila u sam ambijent i u toj palati se održavaju i koncerti, dosta je akustično, iako nismo radili nikakav proračun, ali pravo da vam kažem, odlično izgleda. Inače, tvrđava, kao što sam rekao, ima veliki broj posetilaca, dolaze i kruzeri, dolaze iz inostranstva. Na samoj tvrđavi postoje kao na Kopaoniku na skijanju, imate plavu, crvenu i crnu stazu, u zavisnosti od toga gde se penjete, tako da je veoma zanimljiva i ako imate prilike da dođete, posetite, bit će vam sigurno zadovoljstvo. Hvala.
Let me thank Professor Stefanović for this very interesting presentation of the rehabilitation of this important historical site, such as Golubac Fortress. And if there are any questions, please ask them during the break after the session. Thank you.
The next paper and presentation, entitled Post-Disaster Needs Assessment Methodology, is prepared by Mirjana Laban, Sandra Nedeljković, Željko Žugić i Miloš Knežević. The presenter is Mirjana Laban.
Hello, good morning or afternoon. I think it's nearly afternoon. It's a great pleasure to be here once more again, and I hope these kind of events will go on for many, many years more. It's always a pleasure to see the familiar and the new faces. And first of all, I would like to thank the organization and to Society for Construction Engineers of North Macedonia for this really outstanding event. My paper will be presented in English on the screen, but I would like to talk in our local language because it is not scientific paper as it is. It's a paper which has some intentions to inform local engineers of new possibilities to be included in new business projects and everything what is going on in the contemporary practice these days. Hope you will excuse me who doesn't understand our language, and you can follow my presentation on the slides. Drage kolege, govorit ću sporije, nadam se da ćete me razumeti. Ova prezentacija je namenjena vama koji ste ovde kao inženjeri iz prakse, da vidite koji su novi trendovi i šta je nama potrebno u svim zemljama Zapadnog Balkana, kako da se usavršavamo kao inženjeri, da bi bili korisni, dakle, našoj zajednici i da ne bi morali da uvozimo eksperte sa strane da rade ovakve procene. Ta metodologija se zove Post-Disaster Needs Assessment, znači potreba za potrebama nakon katastrofe koja se desila. Zašto je ona bitna? Iz dva razloga. Zato što države koje budu pogođene ovakvim događajima imaju velike štete i moramo da konkurišemo, naročito mi koji smo slabije razvijeni, za fondove, za evropske i za svetske fondove. Prvenstveno za fondove Svetske banke, Ujedinjenih nacija i Evropske unije. Da bi uopšte mogli da konkurišemo, moramo imati urađenu ovakvu jednu procenu. Kod nas u Srbiji je to prvi put urađeno nakon poplava 2014. i tada su bile poplave u Bosni i Hercegovini i takođe je rađena ovakva procena. Nažalost, nismo imali naših eksperata i radili su ljudi, znači, sa strane, mislim, Francuzi, Italijani i tako dalje. Dostupne su te procene, znači, na netu. Šta se dešava danas usled klimatskih promena? Znači, mi moramo da vodimo računa o tome kako ćemo izgraditi upravo ovakve otporne resilient cities, resilient urban settlements, otporne gradove, otporne zgrade. Potpuno jedan novi koncept ideje opstanka u urbanim sredinama i takođe ideje kako da smanjimo uticaj. Mi ne možemo da sprečimo klimatske promene, niti neke prirodne katastrofe, ali na mnoge od njih možemo da utičemo i možemo da smanjimo posledice određenim preventivnim merama. Kakva je statistika? Vrlo poražavajuća. Ovo je u svetu, što vidite na ekranu, znači u 20 godina, možemo reći, prvih 20 godina 21. veka, imali smo 1,3 miliona ljudi koji su poginuli u katastrofama i preko skoro 4,5 milijarde onih koji su bili povređeni, raseljeni, ostali bez svojih domova. Od toga je zanimljivo da se 90% smrtnih slučajeva desi usled geofizičkih katastrofa, a skoro 80% direktnih ekonomskih šteta i gubitaka dolazi usled klimatskih događaja, znači poplava, oluja i tako dalje. Sendai framework, čuli ste verovatno za Sendai protokol, u stvari ima za cilj da smanji uticaje katastrofa na društvene zajednice. Znači, ovog puta imamo širu sliku. Nije samo da sačuvamo zgrade, objekte, da ih projektujemo prema performansama ili prema propisima, nego je potrebno, znači, da očuvamo celokupnu zajednicu, znači, društvo i ekonomiju, i zdravlje, i ljude, i sve ono što čini jednu jedinicu. Šta je važno? Da prikupljamo podatke o štetama onako kako bi bili uporedivi, jer samo na taj način se neke katastrofe mogu uporediti sa nekim drugim koje se odvijaju. Nije samo naš slučaj da su ti podaci prosto neuporedivi, jer su principi prikupljanja i kriterijumi različiti. Znači, potrebno je na nivou prvenstveno cele Evrope da bi funkcionisala ova pomoć i da bi funkcionisao mehanizam za civilnu zaštitu Evropske unije, napraviti jedinstvena uputstva kako se prikupljaju, znači, podaci nakon katastrofa. Ovo što vidite na slici su opštine koje su u Srbiji bile pogođene poplavama 2014. Kao što sam rekla, nije samo naš slučaj u našim zemljama, da često mi mislimo da mi nismo tako dobri, da su druge zemlje bolje, zapadne zemlje, napredne zemlje, naprotiv. Rađen je screening 2013. godine i ustanovljeno je da za zemlje Evropske unije imamo 62 nacionalne i regionalne baze i da imaju mnogo problema. Znači, da podaci se ne šalju redovno ili odmah, da su nekoherentni, da su nekompletni i da su nekad nepouzdani i da su te baze podataka nisu u otvorenom pristupu, što je veoma bitno. Imamo 44 institucije u Evropi koje to rade, uglavnom su to istraživačke institucije, univerziteti, konzorcijumi i neke nevladine organizacije. Ova metodologija funkcioniše, znači, od sredine 2017. Imamo 55 takvih procena, ali ona funkcioniše od 70. godina i potiče zapravo iz Južne Amerike, gde je prvi put urađeno ovakva jedna kompletna procena, znači šta se sve dogodilo, šta je sve oštećeno, znači šta su direktne štete i šta su naknadne štete, odnosno šta su gubici. Analizirano je 55 u nekom istraživanju ovakvih metodologija i ustanovljeno je da potpuno odgovara kriterijuma Evropske unije, Ujedinjenih nacija i Svetske banke. Neke definicije su nam već poznate, a neke malo treba više da razmišljamo na ekonomski način i da vidimo šta zapravo čini ovakve procene. Znači, prvo da razdvojimo štete od gubitaka. Zatim imamo jednu liniju, obe te, kako da kažem, i Evropska unija i Ujedinjene nacije i Svetske banke imaju u stvari tripartetni sporazum. Ali Evropska unija upravo zbog ovih nekoherentnih podataka ima malo možda i niže kriterijume i takvi podaci se skupljaju recimo u MDAT-u i slično, ko se time bavi, verovatno već i zna. A detaljne instrukcije koje su dale Ujedinjene nacije i Svetska banka su bukvalno priručnici koje možete sve sa tipskim obrascima preuzeti, prevesti i upotrebiti. U Srbiji trenutno se dešava to da se sprema obuka za zainteresovane, znači ovde učestvuju svi, inženjeri svih struka, ekonomisti, pravnici, znači učestvuje jedan širok dijapazon društva i ima mesta, znači, za sve. Najpre za pripadnike lokalne civilne zaštite i javne uprave i oni će prvi biti obučeni da rade ovakve procene i naročito oni koji rade u sistemu, recimo, inspekcijskom nadzoru ili nešto slično. Po evropskoj metodologiji, ono što je, kažem, malo jednostavnije, možemo reći da su izazovi nedostatak standarda i uputstava za prikupljanje podataka o štetama i gubicima i nedostatak, znači, nacionalnih propisa i okvira za tretman tih podataka. Kako se definišu najosnovnije stvari? Ja ću samo biti toliko kratka, uputit ću vas na literaturu da možete sve detaljno pročitati i raspitati se. Oni koji govore engleski jezik mogu da rade u celom regionu, takođe ko govori lokalne jezike, albanski, makedonski, sve varijante srpsko-hrvatskih jezika koje se govore, znači, na našem području, oni takođe mogu da rade u celom regionu. Oni koji govore engleski i druge svetske jezike mogu da rade nakon ovakve obuke kao eksperti za Ujedinjene nacije ili Svetsku banku širom sveta. Imamo direktno pogođene osobe, znači, u ovom što se tiče ljudskih gubitaka, imamo direktno pogođene osobe, što uključuje one koje su direktno pogođeni, znači, ovim događajem i da im je ugrožen fizički integritet. Onda imamo one koje su indirektno ugroženi bili od ovoga, znači oni koji žive u tom području i trpe indirektne efekte od katastrofa. Recimo, ako su prekinuti putevi snabdevanja ili uopšte komunikacije, a vi treba da idete iz jednog u drugo mesto na posao ili su lanci snabdevanja, idu preko te komunikacije saobraćajne, imate veće troškove i morate da idete okolo, je najprostiji primer za to. I smrtni slučajevi, znači oni koji su poginuli i poginuli pronađeni tokom događaja, kao i oni koji nedostaju, znači koji su zapravo ljudi, kako bih rekla, izgubljeni, nestali, broj tih ljudi čije mesto, znači gde su trenutno se ne zna i niko nije stupio u kontakt sa njima. To su 4 kategorije za ljudske gubitke, dok su indikatori štete, znači štete koje su se desile kućama, koje su kuće potpuno uništene, znači kuće, odnosno stanovi koji imaju manje oštećenja, takvog tipa da mogu da se koriste ponovo nakon nekih popravki. Zatim imamo školske edukativne centre, znači oni su bitni, koji su oštećeni ili uništeni tokom katastrofe. Zatim, osim zgrada, procenjuju se takođe, znači ono što je nama najbliže, zgrade izgrađeno okruženje, takođe se procenjuju štete u poljoprivredi, znači usevi i šumarstvo, štete na administrativnim zgradama, znači javnim zgradama u vlasništvu država, industrijskim zgradama, komercijalnim zgradama, štete znači na putevima, železnicama, komunalnim sistemima, infrastrukturi i drugim sistemima koji su neophodne za funkcionisanje zajednica. Ekonomski indikatori razlikuju direktne štete, indirektne gubitke ili štete i one što je neprocenjivo, znači ono što ne možemo da kažemo koliko to košta u novcu, kao što su neke kulturne vrednosti ili nije vidno, znači, u tom kontekstu. Zatim, sektori su grupisani na infrastrukturu, znači voda i kanalizacija, energetske mreže, putevi, saobraćaj i komunikacije, zatim društveni sektor koji obuhvata kuće, odnosno stanove, edukativne i zdravstvene centre i ekonomiju, poljoprivreda, industrija, trgovina i turizam. Ovde u ovoj tabeli se vidi, znači, koji su efekti katastrofe koja se desila u Srbiji i vidite da je ukupno procenjeno na 1.500.000.000, mislim da je u dolarima. Zatim imamo instrukcije koje slede za procenu za izradu ovakvih procena. Znači imamo generalne instrukcije, inicijalne informacije koje su nam potrebne, stanje nakon katastrofe i procenu šteta i gubitaka. Svi ovi podaci takođe su nam potrebni i na makroekonomskom i personalnom nivou, jer ovde sad govorimo i o ličnim, znači, problemima naših zajednica. A troškovi za rekonstrukciju, evo tabela, znači imali smo tamo 1.500.000.000, a ovde ima 1.346.000.000 ili eura, koliko je već bilo procenjeno da je šteta. Znači, postoje neke ukupni štete i gubici koji ne mogu da se iskažu u novčanoj vrednosti i koji su trajno izgubljeni tokom ove katastrofe. Nakon 10 godina upotrebe ovakve metodologije, analizirani su, znači, posebno rezultati 14 studija slučaja, uključujući i procene koje su urađene za Bosnu i Hercegovinu i za Srbiju, i zaključeno je, između ostalog, da ova metodologija obezbeđuje kvalitativno i kvantitativno bogate, veoma podrobnu bazu podataka i da je da su sprovedene znači na jedan prihvatljiv način, tako kako da bi to kraće rekla. Međutim, ono što se pokazalo kod nas na Balkanu tokom ovih poplava je da predviđeni rok za izradu od 6 do 12 nedelja ovakve procene je moguće uz intenzivne napore i dobru koordinaciju skratiti na svega 3 do 4 nedelje. I mi smo vrlo brzo imali donatorsku konferenciju. Ako se sećate, poplave su bile u martu, a donatorska konferencija je bila već u junu mesecu. I već je tad Srbija dobila značajna sredstva, znači koje je upotrebila za obnovu. Eto, toliko htela sam to da vam ispričam i da vas upoznam sa nečim što sledi. Nadam se da ćemo pokazati da i mi imamo naše eksperte i stručnjake i da nije potrebno da za ovakve poslove uvodimo znači, strane eksperte koji i slabije poznaju teren. Znači, realno, najlakše je neko ko je iz lokala da uradi ovakvu jednu procenu nakon katastrofe. Hvala vam na pažnje. Thank you for your attention.
The topic of the last presentation in this session is fire resilience and buildings sustainability in renovation wave. It is prepared by Suzana Draganić, Mirjana Laban, Igor Đolov, Merit Cvetkovsa.
Thank you very much for the introduction. First, I would like to give a short introduction to sustainability and fire resilience in order to link sustainability and fire resilience, so we will hear what we mean by that. The concept of sustainable development actually derived from 1987 and evolved with the time and shifted more to social development, economic development, and environmental protection for future generations. The term resilience has been around for centuries. There are traces of the use of the term already in 1625. In 2008, the UN Office for Disaster Risk Reduction came up with this definition that provides more holistic approach that includes actually systems, communities, and society, and not only one domain as resilience goes beyond physical resistance to hazards. Fire resilience is often seen as the ability of a building to withstand the effect of fire. However, fire resilience is much more than that, as fire has an impact on economy, community, and environment. So here we also have to have a holistic approach and to consider more than one aspect. So what is the link between fire resilience and sustainability? Designing sustainable buildings requires considering a wide range of aspects that affect society, environment, and the economy. This actually resonates well with the concept of fire resilience, as fire can have a dramatic impact on all three dimensions of sustainability. So in order to be sustainable, buildings must be fire safe and fire resilient. So a building is not sustainable if it's not fire resilient. This actually can be pictured in this way, where a sustainable and fire resilient building is safer building that is able to achieve sustainability targets and fire resilience targets. It is also obvious from the picture that finding a suitable balance between sustainability and fire resilience objectives can be particularly complex due to the multidimensional aspect of each. So why this is actually important? Why the sustainability and fire resilience are important? I think that these facts and figures actually say it all. Over the years, we have witnessed many building fires with catastrophic consequences, which taught us that fire resilience is a very important part of sustainable construction. Despite this, so far fire resilience is not a part of any of existing sustainable building rating schemes. However, building fires that have happened on high-rise residential buildings have led to re-examination of existing methods for evaluation of fire performance of buildings and their components. Significant efforts have been made in Europe to improve this process. However, development of fire safety rating scheme for building is an early stage activity. In 2018, through revision of Energy Performance Building Directive, European Union actually acknowledged the importance of addressing fire safety through energy renovation of buildings. It is emphasized that fire safety of the building should not be compromised by energy renovation. So energy renovation is actually a good starting point to tackle both the energy efficiency requirements and the fire safety challenges. Improving a building energy performance through renovation can make a building more sustainable, but can also increase the fire load of the building and change the way the building responds to a fire. So the Renovation Wave is actually an initiative that is from 2020 aimed to accelerate the renovation of existing buildings across the European Union and make them more energy efficient, sustainable and resilient. The initiative prioritizes actions in 3 areas: tackling energy poverty and worst performing buildings, renovation of public buildings, and decarbonization of heating and cooling. As part of its Renovation Wave strategy, the European Commission proposed introduction of minimum energy performance standards for the worst performing buildings that actually factors in fire safety. Actually, this ongoing EPBD revision holds immense potential to shape the future of European building stock towards sustainability and safety. By acknowledging the significance of fire safety in conjunction with energy efficiency, the revision can pave the way for resilient, decarbonized, and safe buildings. In the end, I just want to show you the current situation in Serbia. As a member of energy community, Serbia is obligated to implement EU directives related to energy efficiency and energy performance of buildings in international legislation. And in 2022, the long-term strategy for inciting investments in the renewal of the National Building Fund until 2050 was adopted. The main goal of the strategy is to define renovation measures. 5 possible scenarios of renewal were prepared, and it is emphasized that renovation measures must not impair fire safety of buildings. So, conducted research indicates that fire resilience is one of the crucial aspects of overall building sustainability, yet it is often neglected or inadequately addressed in existing sustainable building rating schemes. So in order to create safer and more resilient, more sustainable built environment, there is a need to adopt a holistic approach to building sustainability through integration of fire resilience from initial building design and into building policies and regulations. I try to be fast, so thank you very much for your attention.
Thank you for your presentation and minding the time frame. Before we close, are there any short questions? No? Yes? Yes, here in the back.
Hoću da postavim pitanje za Tvrđava Golubac. Ne znam je li tu profesor? Nije. Nije tu ništa. Naći ću ga.
Try to find him during the break, okay? Okay, so we end this session. Enjoy the lunch break. See you in the afternoon. Thank you.